I'm going to run through inclined plane, and it starts off looking at weight and mass, which we're quite used to using. I always use an FW, but your syllabus in the textbook, I just noticed, use an FG, so the force of gravity. Mass times acceleration due to gravity, 9.8. So that's pretty easy. We've done that for 2 years. Normal force. Syllabus does specify that you can define what the normal force is. So the normal force acts against the weight. If you didn't have it, it's like Newton's third law, action and reaction. If you didn't have that normal force pushing up, then the object would sink through the table. So the normal force, the important thing about it is it's perpendicular to the surface. So when we get on to inclined planes in a minute, it's not exactly opposite the weight. It's on an angle. Don't need that. Friction and tension. Main thing about friction is it opposes the motion. It's a force, so it's measured in newtons. If there's no acceleration going on, that means whatever force is pushing it and the frictional force which opposes that motion are equal. You've got to have a net force to get acceleration. So over here in these little diagrams, the force of friction is the same size as the horizontal force. So that will be a constant speed, or it might be at rest, might not be moving. That's still a constant speed. There's no net force there because they balance each other out perfectly. This one, this force, the horizontal force, is greater than the friction force, so there'll be a net force of 10 newtons there. That 10 newtons will accelerate it in that direction. And in the worked example here, they use that diagram and they say the mass is 3 kilos. So you get the net force, and then you use F equals ma with the net force to get the acceleration. Don't forget your acceleration has a direction to the right. There's quite a few pages here then on tension. The syllabus doesn't specifically mention tension. It just says solve problems involving force due to gravity and mass using the mathematical relationship between them. And then define normal force, describe and represent forces acting on an object on an inclined plane through the use of free body diagrams. So that's just a diagram. And calculate the net force on an object on an inclined plane. So no need to get into, I don't think, all the tensions to do with pulleys and whatever. Just very basically here, we've got the weight, the force of gravity acting down, and then there's a force in this, a tension force in this rope. If this isn't moving, they're balanced, right? So, or I suppose it could be moving at a constant speed, but they're balanced. That's all there is to it. So they're all the same. Then they start going on angles, but I think you'd be better to concentrate on inclined planes, which are mentioned specifically. Tension isn't mentioned. All right, so we're on to our inclined plane. So we've got our object on an inclined plane. The force of gravity acts straight down, and that's not very useful to us. So we split it into two components. One component is perpendicular to the surfaces here, and the normal force, Fn, will be equal and opposite to it. And the other force that's useful to us is the force that's acting down the plane. This is the force that friction will act against, and this is the force that might end up accelerating the object down the plane. Through the wonders of geometry, this angle here in the plane is that angle up in there in the diagram. So we can work out our components. So I've just taken that little drawing and redone it there. Some old hags. So sine theta is the parallel component divided by the weight, Fg. Rearrange. F parallel is Fg sine theta, and F perpendicular is going to be Fg cos theta. Here, it won't be long. Righto. So we've got this situation now. We've got two forces These ones, we're not worried about them. They're not doing anything much for us. These are the ones we're interested in. The parallel component down the plane and the force of friction, which will oppose it. So if they're equal, there's no net force, so you're not going to have any kind of acceleration. It's either just going to sit there or it's going to slide down at a constant speed. So look for that constant speed. If it says it's a constant speed, you know that the force of friction equals the parallel force. If the parallel force is bigger than the force of friction, there's going to be a net force. So there'll be acceleration down the slope, and F net equals mass times acceleration. So you can work that out. Righto, I slipped across then. I really don't see the point in doing all this pulley stuff. Then if you've got spare time when you're studying, you can have a look at that. Don't forget to have a look here at the review at the end in case there's any points that I've missed that were important. Let's have a look at number 23. It's a 3-star one again. So we've got this guy, he's pulling this box up this incline, and to make it a bit more complicated, he's pulling it at an angle here. All right, now here's the golden ticket, constant speed. So that tells me that the force of friction and the parallel force, which would be acting down here, are being balanced by him pulling. But it won't be this force here in the rope because of the angle. It will be the component of the force that's parallel to the surface here, to the plane. So let's have a look. Here he is. So acting down the plane, I've got the force of friction and the parallel component. And because it's a constant speed, I know that this force here is going to balance them. So first of all, it tells me the force of friction is 650. I need to work out this component here, the old FG sine theta that I showed you up there, FG sine theta. You get it from this. Sine theta is the force parallel divided by the weight, FG. Right, so down here, FG is mass times 9.8, rightio. 980 sine 35, 562 newtons. So that means we've got a total 562 plus 650 of 1,212. It's a constant speed, so I know that it's balanced. So the total force to balance that plus that is going to be 12 up the slope. Now we've got to remember the rope is on an angle, so we're not finished. We've got to, that 12 is this component here. We've got to reverse engineer that to work out what force he's pulling on the rope at. So the old sine, no, cos, can, adjacent over hypotenuse. So the cos of 20 is going to be the adjacent side divided by the hypotenuse. The old swapperoonie. So he's actually pulling on that rope with a force of 1,290 newtons. And that's the answer.